Alright, so welcome back. Today we are going to be talking a bit about collisions and impulse. So starting with what we talked about last time, force equals the change in momentum divided by the change in time. If we break that down, the change in momentum is a mass times the final velocity minus the initial velocity, all divided by the change in time, which is the final time minus the initial time. So what we want to talk about here is impulse. Impulse is the change in momentum. That's literally how it's defined. It doesn't have a special symbol. It's just a delta P, change in momentum. So if we take this first equation that we had and we do a little bit of multiplication, cross multiplication, you love algebra, we've got impulse equaling a force times a change in time. And its units are force, newtons, times time. The concepts of this section really are that simple. Delta P equals F times delta T. So let's go ahead and hit up a problem. Problem being, calculate the impulse experienced when a 70 kilo person lands on firm ground after jumping from a height of 3 meters. So this is just them jumping down. Well, first off, we are going to need to figure out a velocity. Yay, kinematics. So remember our equation, v squared equals v naught squared plus 2 times acceleration times our y final minus our y initial. Well, we can say right off the bat here that our our initial velocity is going to be 0, and then our final y position would be 0. Taking the square root of that, we are going to be left with velocity equals the square root of 2 times acceleration times the negative y naught. Alright, let's plug in some numbers real quick. We have the square root of 2 times a negative 9.8 meters per second squared times a negative 3.0 meters. Plug that into your calculating machines and you're going to have a velocity equal to 7.67 meters per second. Alright, we need a little bit more room here. Okay, so what is impulse? Impulse, delta P, is going to equal mass times delta V, correct? So our mass is going to equal 70 kilograms times our change in velocity, so 0 meters per second minus 7.67 meters per second. We're going to have an impulse equal to a negative 537 Newton seconds. Now this is negative because it's going in the negative direction. Okay, so let's look at part B of this question. Estimate the average force exerted on the person's feet by the ground if the landing is stiff-legged, 1 centimeter of body movement. So the collision is going to happen very fast. We can assume the upward force is going to be constant simply because the problem says firm ground. So our velocity is going to simply be the average velocity, v final minus v initial all over 2. And that would be 7.67 meters per second minus our 0 meters per second divided by 2 will equal 3.83 meters per second. Now I'm keeping all of these numbers in my calculator and there's a bunch of extra digits floating around here. So why did I calculate the average velocity? Calculated the average velocity because I'm going to need to know the change in time. And the change in time would just be a distance traveled divided by that average velocity, which is going to be in this case 0.01 meters divided by 3.83 meters per second. Throw that in your adding machine and you are going to get a 2.6 milliseconds. That's roughly 2.5 thousandths of a second. Alright, force. We're asked force in this equation. Force is going to be equal to our impulse divided by the change in time. So we have a negative 537 Newton seconds divided by 2.6 milliseconds, and that's going to equal a force of approximately 205,000 800 newtons, and that's in the downward direction. That's huge. But we can't forget we need to add a little insult to injury, because also in this direction we have gravity. So the question asks us about the force of the ground. The force of the ground pushing up is going to equal gravity, mass times gravity, pulling down. It's also going to equal our impulse force pulling us down. So let's add that up real quick. The force of the ground is going to be our mass gravity, so it's going to be 70 kilograms times our gravity, 9.8 meters per second squared, plus this astoundingly huge number we found a moment ago, 205,800 newtons, to give us a sum total of 206,500 newtons. That's going to break some bones. So let's figure out what happens if we try to bend our legs when we fall. So part C is estimate the average force exerted on the person's feet by the ground if landing with bent legs. So we're going to assume the body got squished down half a meter, 50 centimeters. So in this case, our delta T is just going to be equal to the distance divided by velocity, same velocity we found before, the 7.7 divided by 2. So that's going to equal 0.50 meters divided by, what do we have, 3.83 meters per second, and that's going to be approximately equal to 0.13 seconds. So the force on this, remember our force is going to be our impulse divided by time, and that would be the negative 537 Newton seconds divided by our new delta T of 0.13 seconds. Now we're getting something much more reasonable. 4,116 newtons going down. Okay, so remember the force of the ground that we're looking for is going to equal the force of the normal plus the force of the impulse. So that would be 4,116 newtons plus 686 newtons to give us a total of approximately 4,800 newtons. Now that's still a lot. That's several times a person's body mass, but it shouldn't break any bones. So be sure when you're jumping to bend your legs. Also, please be sure to finish the rest of tonight's assignment, which is on As You Learn, and thank you for watching.